Hello everyone, in this video we will be discussing about the computer science question paper of ISRO Scientist Engineer, which was held on 17 December 2017, and in this we will be discussing questions 51 to question 60. So let's move on to the questions. It is the 51st question. Suppose the numbers, their given numbers are inserted in any order initially into empty binary search tree, okay, and the binary search tree uses the reversal ordering. So what we have to remember is it is the reversal ordering on natural numbers. That is, 9 is assumed to be the largest number, smallest number, and 0 is assumed to be the largest number. Okay, the in-order traversal of the resultant binary search tree is, okay. So there are two ways to solve this. You can either solve by making a binary search tree from this, okay, and after that you can take the in order. But there is a property of binary search tree, you have to remember that is the in order traversal of the binary search tree will always give the ascending order or increasing order, will always give the ascending order or increasing order. Okay, this is a property of binary search tree, or just you can say it is the property of in-order traversal. That is, in-order traversal of a binary search tree gives the element in increasing order. Okay, if in a case it is given the binary search tree uses a reversal ordering, means here the answer should be 9 should be the lowest number and 0 should be the highest number. So our option would be D, that is 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This should be the answer because the in-order traversal of a binary search tree gives the element in increasing order. So D is our answer. Okay, next move on to the next question. A priority queue is implemented as a max heap. So here we have a queue which is priority queue which is implemented as a max heap. Now what is a max heap? Max heap is a heap in which the root element, that is the root element, is greater than the child element, both left and right child. That is, the parent is not the root, or the parent is greater than both the left and right child. Parent is greater. Okay, this is the property of max heap. Okay, so our max heap, initially it has 5 elements and the level of order of max heap traversal is this, that is 10, 8, 5, 3, 2. So this is our max heap which contains 5 elements. Okay, we have constructed the max heap by given it. See, 8 is the parent of 3 and 2 and it is greater than both 3 and 2. 10 is the parent of 8 and 5 and it is greater than both 8 and 5. Okay, so this is a max heap, and now what we are doing is 2 new elements 1 and 7 are inserted into the heap. So we have to insert 1 and 7. So let's insert 1. When we insert 1, so 1 would be here, 1 is inserted over here. Okay, so see, let's check if the property of max heap is maintained or not. 8 is greater than 3 and 2, 5 is greater than 1, and 10 is greater than 8 and 5. Yes, so there is no problem. Okay, after inserting 1, this is the proper heap. Next we have to insert what? Next we have to insert 7. So when we insert 7, we would be inserting 7 over here. Okay, so 7 would be here. So again we would be checking about the property of the heap. That is, 7 is inserted over here. We will be checking the property of the heap. That is, 8 is greater than 3 and 2. There is no problem. Property maintained. 5 is greater than 1 but it is less than 7. Here we have to maintain the heap property here. So what we would be doing is we would be swapping 5 and 7. Okay. Now this would be after swapping 5 and 7 we would have this. That is, 5 is swapped with 7. Now we would check. 8 is greater than 3 and 2, yes. 7 is greater than 1 and 5, yes. And 10 is greater than 8 and 7, yes. So this would be our answer. The process of swapping this, that is maintaining the property of the heap, is known as heapify. It is called maintaining the heap property. Okay. So this is heapify. After heapify, our sequence is, it is 10, 8, 7, 3, 2, 1, 5. So this is our answer. That is answer D, 10, 8, 7, 3, 2, 1, 5. Okay, this was all about priority queue, max heap. Next one to the next question. Okay, a minimum number of stacks required to implement a queue. See, the queue is first in first out data structure. So suppose we have a queue. In this we have 2, 3, 4, 5 and 6. Okay, let this be a queue. This queue, and in this queue it is 0, 1, 2, 3, 4. Okay, so first we have inserted 6 then we have inserted 5, then we have inserted 4, then we have inserted 2, and we have inserted 3 and 2. Okay, in Q, deletion takes place from the front. That is first in first out. Q is first in first out data structure. That is 6 was inserted first, so we will be deleting 6 first. So in order to implement this, so we need to have 2 stacks. How? See, push 6, push 5, push 4, push 3 and push 2. If I have one stack, then when popping, and this is the top of the stack, while popping I will get 2 first, but I want 6 first. So I'll require one more stack and push all the elements of this stack to this stack. That is 2, 3, 4, 5 and 6. Now when I pop, that is 6, then 5, then 4, then 3, then 2. This is equal to this Q. So we would be requiring 2 stacks to implement a queue. Okay, next question. A strict binary tree with 10 leaves. Okay, we have 4 options. Cannot have more than 90 nodes, has exactly 90 nodes, exactly 70 nodes, exactly 20 nodes. Now what is a strict binary tree? A strict binary tree is a binary tree where every node would have either degree 0 or degree 2. Never degree 1. That is a binary tree which has either, every node has either 0 child or 2 childs. Let's say example, see, this is a strict binary tree. Okay, these are the internal nodes, 1, 2, 3, 4, 5, 6. These 7 are the internal nodes, and every node, that is a root node, has 2 child. These internal nodes all have 2 childs, and the leaves have no child. So this is an example of a strict binary tree. So now we are talking about a strict binary tree with 10 leaves. Here we are having 8 leaves. Okay, so we need to have 10 leaves. So this may be our binary, this is our binary tree which would be having 10 leaves. So see, now we are having 10 leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We are having 10 leaves. So it can have 10 leaves and 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 intermediate nodes. So 10 leaves plus 9 intermediate nodes, total of you would be having 19 nodes. So it has exactly 19 nodes. This is our answer, but we have a formula to solve this also. See, this is the formula. A strict binary tree with L leaves. So here we have 10 leaves. L is equal to 10. Always contain 2L minus 1. That is 2 into 10 minus 1 nodes, which is equal to 19 nodes. So see, it is easy. We have a formula over here. Okay, so the answer is B, has exactly 90 nodes. Sometimes it can be asked, a strict binary tree with the 9 internal nodes. 9 internal nodes has how many nodes? So there is a formula for that also. A strict binary tree with I internal nodes always contain 2I plus 1 nodes. Okay, see, in this example also we have 9 internal nodes, 2I plus 1 nodes. So we have 9 internal nodes. So 2 into 9 is 18. 18 plus 1 is 19. So we have a total of 19 nodes. So whether it is asked in the terms of leaves or it is asked in the terms of internal nodes, we have 2 formulas to calculate the total number of nodes. Okay. So let's move on to the next question. What is the height of any AVL tree with 7 nodes? Assume the height of the tree with a single node is 0. Okay, now before moving on this, we should know what is the AVL tree. Okay, so AVL trees are binary trees and they have the following restrictions. The height difference of the children is at most 1. That is, it should be 1 or this should be less than 1. And both the children are AVL trees. So these are the properties of AVL trees. So let us construct a AVL tree with 7 nodes. Okay, first node is okay. I am giving a child, 2 childs. Okay, so this is the first node and there are 2 childs. This is height 0. Okay, next. Here we have the height is 1. Here we have the height is 1. So height difference is 0. 1 and 1. 1 minus 1, height difference is 0. Now here I am inserting one more node. Okay, so here height of this is 1 and 2 and here height is 1. So 2 minus 1 is 1. So this is also no problem. But if I want to insert one node here, So then the height is 1, 2 and 3. Here the height is 1. So I can't insert a node here. So I would be inserting a node over here. Okay. So now the height difference is 1, 2. 2 minus 1 is 1. There is no problem. Okay. I can't insert a height over here till now. But if I insert a node over here, then I can insert this over here. Okay, so this is 1, 2, 3, 4, 5, 6, 7. We have 7 nodes. This is a ABL tree with 7 nodes, and the height of the tree would be 1, 2, and 3. 3 would be our answer. So for this also, if we have n nodes, we have a formula for that. Okay, so 3 is the answer. If you have n nodes, we have a formula for that, and the formula is h of n. For n nodes, it would be equal to h of n minus 1 plus h of n minus 2, height of n minus 1, height of n minus 2 plus 1. This is the formula. So in the C, the height at the number of nodes at 0 is 1. At 0th level, number of nodes at 0th level is 1. So h of 0 is 1. Okay, and h of 1 would be h of 0 plus 1. So we can see it like this only. We have 2 nodes, 1 and 2. Okay, we have 2 nodes at level 2. So h of 1 would be 2. Now we have to calculate for h of, like this we would be calculating. See, in our option, we have 3 and 2. So 2 is not the answer. Let us calculate for 2 also. We have to calculate h of 2. So h of 2 would be h of 1 plus h of 0 plus 1. H of 1 is 2, h of 0 is 1 and plus 1, which is equal to 4. But here we have 7 nodes. Here we have 7 nodes. So h of 2 is not the answer. So 2 is not the answer. Okay. Likewise, we can try it for h of 3. It is equal to h of 2 plus h of 1 plus 1. H of 2 is 4, h of 1 is 2 and plus 1, which is equal to 7 nodes. So in our question, we have 7. So like this, we can try for each option, that is 2, 4, 5 and 3. So this is a formula from which you can calculate if the number of nodes are more. But if the number of more nodes are less, you can construct a ABL tree like this. So answer is B, that is 3. Next question. Which of the following property is correct for red-black trees? So before moving on this, we shall go to the properties of red-black tree. What is a red-black tree? Okay. So a binary search tree is a red-black tree. Okay. A red-black tree is a binary search tree. That is a binary search tree with one more attribute added. That is the color of the nodes would become a red-black tree. The first property of the red-black tree is every node is either red or black. Okay, we will check simply the path. If a node is red, if the node is red, every leaf node is red. Okay, it is not an option, but you have to know that every node has some color. Next, every leaf is black. So we are talking about the leaf node, and leaf is black. Leaf node is a sentinel node. It is called a sentinel node. It is also called sentinel node. So every sentinel node is black. So it is in our option D. So our option D is true. Every leaf, is false, because here it is given red. Every leaf is black, so it is false. Next, if a node is red, then both the children are black. Okay, here it is. If a node is red, then both the children are red. No, it is also false. So you have to remember the properties of the red-black trees. Next property is every path from a node to a descendant leaf contains the same number of black nodes. Every simple path from node to descendant leaves contains the same number of black nodes. Yes, this is true. Okay, so this is our answer. Okay, it is our answer. And if a node is red, then both children are black. This is also false. Because if the node is red, both children would be black. But here is one is red and another is black. So this is false. Both are red is also false. So the answer would be A. That is, every simple path from a node to descendant leaf contains the same number of black nodes. So A is our answer. So you have to remember these properties. The in-order and pre-order traversal of a binary tree are this and this. the post-order traversal of a binary tree. So we are given an in-order and pre-order traversal. We have to calculate the post-order traversal. Okay. So for in-order we have left, root, right. That is, root would be in the middle, and we are given pre-order. In pre-order, we have pre means root would be in the front, root, left and right. So in pre-order, the first element is the root. So what is a pre-order? This is our pre-order and this is our in-order which is given. So A would be the root of our tree. Okay, binary tree. So we would be writing A over here. So in in-order traversal, A is over here. So this part would form the left part of the tree and this part would form the right part of the tree, because in order, root would be in the center. So here we would be having D, B, E, and here would be having F, C and G. Okay, now we would again go to the in order. Okay, in order, here C, next is B, so B would be the root. So we have A, okay, B would be the root, and left of B would be the root, and this would be left and this would be right. Left of B would be D and left of right of B would be E. Okay, next B, D and E we have finished. Then we have C. That means C is the root now. Okay, that means C is the root now. C is the root now. So C would be over here, and left of C, from here we would see left of C is F and right of C is G. So here it would be F and it would be G. So this is our answer. So we have to calculate the post order. In post order we have left, right and root. So we would be traversing like this. So when we go to left, it is D, right is E, root is B. So we have completed this left portion. Now left is F, right is G and root is C. So we have left, we have right and the root is A. So answer is D, E, B, F, G, C, A. That is, C is our answer. Okay, so this is how we can calculate for any question. It is the easier one, but even if it is very tough or different, it is given numbers also, then also you can calculate post order from in order and pre order, or if in order and post order is given, you can calculate pre order, but in order is must. We should have in order with us. Next, a virtual memory system uses FIFO page replacement policy. This is one of the most common page replacement policy, and allocates a fixed number of frames to the process. Consider the following statements. Okay, before proceeding, let's see what is FIFO page replacement algorithm. Okay, FIFO is first in first out. In this, the operating system keeps tracks of all the pages in the memory in a queue, and the oldest page in the front of the queue, okay, is taken. When a page needs to be replaced, the page at the front of the queue is selected for removal. That is, it is based on first in first out. The page which comes first in the memory, it would be taken. Okay, but first in first out page algorithm, it suffers from an anomaly which is known as Belady's anomaly. You have to remember this, Belady's anomaly. And what this anomaly says is that states that it is possible to have more page faults when increasing the number of page frames. That is, increasing the number of page frames allocated to the process sometimes increases the page fault rate. Sometimes it is a possibility. It is not always. It is sometimes. It depends on the sequence of frames. Sequence of pages. It depends on the sequence of pages. So sometimes it can increase the page faults. So this is true. Okay. Second, some programs do not exhibit locality of reference. Okay. Locality of reference, it is exhibited by the program which has loop in it. Okay, and it is very easy to write a program without loops by using jump statements. Without using loop, we can use jump statements. So for that, locality of reference is not needed. So this is also true, but these both are independent statements. They are not dependent on each other. They are independent statements because Belady's anomaly, it is caused due to sequence of the pages. It is therefore some of the sequences, but not all sequences. So the answer should be both are true, but n is not the reason for m. They are not the reason for each other, they are independent statements. So 58B is the answer. Okay, next question. Consider 3 CPU intensive processors. We have 3 processors, let them be P1, P2 and P3. Okay, and we have which require 10, 20 and 30 units of time. So the burst time is given, it is 10, or you can say the execution time, it is 10, 20 and 30, and the arrival time I'll write it as 80, it is given as 0, 2 and 6. Okay, how many context switches? You have to calculate the context switches are needed if the shortest remaining time first is implemented. Okay, the context switch at 0 is included, but at the end it is ignored. End is ignored, 0 is included. So let's draw a Gantt chart for that. Okay, at 0 only process P1 arrived. So first context switching takes place over here. Okay, at 0. Because we have to include it. Okay, see, we have to solve it by shortest remaining time first. Okay, till 2 there is no process, so process P1 would run till 2 individually with no intervention. At 2 we have P1 and P2. Okay, the remaining time for P1 is 8 and for P2 it is 20. So shortest remaining time is 8. So we would be using this only. So P1 would run till 6. So it will run till 6. P1 would run till 6. No context switching has occurred. At time is equal to 6, we have P1, P2 and P3. Okay. For P1 we have 2 times remaining, 2 units of time remaining. For P2 it is 20, for P3 it is 30. Still this one P1 would run because it has shortest remaining time. So P1 would run till 2 and 6. It will run till 10. Okay, here it is 4, sorry, 4 remaining. Here will run till 10. This is for P1. Now after 10, we would have only 2 processes, P2 and P3. Now here the context switch will occur. The second context switching will occur when P1 has finished and P2 would start. So it would run for 20. Okay, that is till 30. Okay, and the third context switching will occur when P2 has finished its execution and P3 has started. Okay, so we have 1, 2 and 3. 3 context switching there. In the end we would ignore. Okay, so we have 3. C is our answer. Okay, next question. A process execute the following code. Okay, this is the code. This is the logic of fork. Whenever a fork is called, a child process is created. Okay, so now we have a loop from 0 to n minus 1. It runs from 0 to n minus 1. Okay, whenever a fork is called, a loop would be created. Okay, when for f is I equal to 0, we would have one process created, one child process created for this fork. Okay, first when I equal to 0, it would run. Okay, when it becomes I equal to 1, we have 2 processes. Okay, for I is equal to 2, we have 4 processes, F2. We have 4 processes, and so on. We would be having 8, we would be having 16, and so on. So it is 1 to n minus 1. For I is equal to 1 to n or 0 to n minus 1. So our answer would be 2 to the power n minus 1 processes. Okay, so this would be answer. The answer is D. Okay, so this was all about this part. If you like this video, please click the like button and share, and please subscribe our channel. Thanks for watching.